Hello physics nerds, and this is the review video for the IA number 3 practice exam. There are 18 questions on this sheet, front and back, but they pretty much cover the gist of what you need to know for the 20 question IA, 21 questions for the honors version. Alright, so number 1. A 1.0 kilogram rubber ball traveling east at 4 meters per second hits a wall and bounces back toward the west at 2 meters per second. Compared to the kinetic energy of the ball before it hits the wall, kinetic energy of the ball after it bounces over the wall is... Alright, that's a mouthful. What we essentially need to do is get the kinetic energy values of both scenarios. So I'm going to label this KE1, 1/2 mv squared equals 1/2. 1 kilogram times speed of 4 meters per second. Alright, that's squared. Don't forget to square that. So 16, half of that is 8 joules. The second scenario, 1/2, still 1 kilogram. This time 2 meters per second. Going west, squared, 4 is half of that. So the new kinetic energy is 1/4 as great as the original. Okay, number 2. When a mass is placed on a spring with a spring constant of that, alright, so let's... Here our mass, well, we're looking for energy, PES. So this equals 1/2 kx squared, looking at our problem. Spring constant of that, that's our K. 60 newtons per meter, that's our K. The spring is compressed this much, that's our X value, that's the compression distance. 0.707 meters, don't forget to square that. And we're looking for how much energy, that's PES. When you solve that, you should get 15 joules. That should be a 15, whatever that looks like, it's not a 15. Okay. Number 3. A 50 kilogram student runs up a staircase to a floor that is 20 meters higher, looking for the power output P. We have the mass of 50 kilograms, a distance of 20 meters, and a time of 7 seconds. Power is equal to work over time, but if you expand work to equal force times distance over time, that's what we get. Now the force that you exert while going up the stairs is equal to the person's weight, so we could expand that to mg times d over t. So our mass is 50 kilograms times 9.81 meters per second squared times our distance of 20 meters. Over a time of 7 seconds, you should get a power output of 1,401 watts. This is close to choice C. Alright, number 4. A force of 60 newtons changes the momentum. So here we have a force of 60 newtons. Oops, I misread that. That's 6.0. Changes the momentum by that much. So delta P, change in momentum. 3 kilograms meters per second. We're looking for how long. How long did the force act? So that's a time. Now looking at this over here, where impulse is equal to F times T, which is equal to M delta V, which is equal to the change in momentum. We only need to extract 2 of these. They're all equal to each other, but we only need to use 2 of them. We use this and that. So delta P is equal to F times T. 3 is equal to 6 times T. T is equal to 0.5 seconds. Alright, number 5. We're looking for the total work done on the box by the 20 Newton force. And then move the distance of 2 meters. So work is simply force times distance. 20 newtons times 2 meters equals 40 joules. That's it. Number 6. What is the kinetic energy of that skier? He has a mass of 55 kilograms, traveling at a velocity of 9 meters per second. Don't forget to square that. So 81 times 55 times half. Okay. And you should get 2,227.5 joules. That's as close to choice A. 2,200. Number 7. All right, this could be a little tricky if you don't get messed up with the wording. Okay, so you push a box. You do work to it. Where the work you put into it is 15 joules. So you're pushing it, you release that 15 joules. But if you're doing work on the box, that box gains your energy. So you do work equals release. Where did that energy go? So if work done on box is the same as being absorbed. So that box absorbed all of that 15 joules to it becomes kinetic energy. So work transformed into kinetic energy. This also goes into the work kinetic energy theorem, where the change in kinetic energy is equal to the work done. So you push a box, it accelerates from work into kinetic energy, 15 joules. All right, number 8. So this one's a reading question. A shopping cart slows down. So we're looking at kinetic energy decreasing as it slows down. So that's crossing off A and B. And it says along a level floor. So PE is constant because it only changes if you change the height. So we're looking for gravitational energy remaining the same. That's choice D. All right, number 9 goes into electrostatics. So we need to know what elementary charge is. A particle could have a charge of what? So possible charges have to be whole number multiples of 1.6 times 10 to the negative 19 coulombs. So looking at each of these choices, we could cross off those that are greater than that. Less than that, sorry. We're going to cross off those that are less than E, because E is the smallest possible charge. So A and B we can cross out. That leaves us with C and D. We're looking for a whole number multiple, because we can only go up and down by increments of 1.6 times 10 to the negative 19. All right, so let's do 3.2 divided by 1.6, because they have the same exponent. We could check that out for now. So that's equals to 2. That's safe. 4.1 divided by 1.6 is not a whole number. So it's going to be 3.2 times 10 to the negative 19, which indicates that 2 elementary charges equals that. All right, number 10 is kind of tricky. So here we have a box starting at the top. It's released from rest. So from at the top, all we have is max potential energy. That's all it has. As it goes down the incline, heat is generated because of friction. So that means it's probably going to lose some of that potential energy to internal energy. So potential energy is equal to mgh. Mg is already 40 newtons. And the height is 8 meters, so this is 320 joules to start off. To start with. Next, what you're going to think about is we're going to set this equal to our total energy. So this is all our total energy to start with. So as it slides down the incline, potential energy is transformed into both kinetic energy because it's moving, and to internal energy, Q, because heat is generated. Okay, so we should end up our sum of kinetic and potential and internal energy, the sum of kinetic energy and internal energy should still equal 320 joules. So if this right here is already 50 joules, that means this over here has to equal 270 joules to still add up to 320 total. Now, if you guys did the lab where you roll the marbles down the incline, you calculated for potential energy at the top. According to conservation of energy, we should expect to see that same value when you calculate the kinetic energy at the bottom of the incline. Now, you probably end up with values less than that. Now, why is that? Because you hear sound and there's also heat being generated because of friction. So some of that energy discrepancies is probably due to internal energy, Q. All right, number 11, gravitational potential energy. PE is equal to mgh is dependent on mass, the acceleration due to gravity. Well, it's constant because we're still on Earth, with respect to Earth, so it doesn't change. Cross that off. And h, height. The only one that fits that is position. Position is the same as the height, vertical position. All right, a constant force is used to keep a block sliding at constant velocity. So for number 12, constant V means constant kinetic energy. Along a rough horizontal track, so PE is also constant. As the block slides, there could be an increase in its internal energy only. If you think about it, if our kinetic energy and potential energy are staying constant, the only thing that could be increasing is the internal energy only. All right, let's go into number 13. All right, 2 kilogram ball traveling north 4 meters per second collides head-on with a 1 kilogram ball traveling south at 8 meters per second. So this follows conservation of momentum. Total momentum before equals total momentum after. So P before equals P after. Okay, we don't know what's happening after. That's what we're looking for. So first we start off with breaking this down into, we don't know what's happening after. We're looking for the total momentum after, so we could just leave it like that. We're going to label this as object 1. So going north. Object 2 is 1 kilogram. It's traveling 8 meters per second southward. So that's a negative. Remember, this is vectors. Oh, look at that, equals 0. I guess they come to a stop afterwards. Okay. Number 14. A 1 kilogram rock is dropped from a cliff 90 meters high. After falling 20 meters, the kinetic energy of the rock is approximately, okay. So here we have a rock 90 meters high. This is the ground 0 meters. And so the rock keeps falling until it hits the 70 meter mark after 20 meters. All right, so it fell about 20 meters. So within that 20 meter interval, it gained kinetic energy. So here we have a max of potential energy at the top, mgh, 1 times 9.81 meters per second squared times a height of 90 meters. Okay. And you should get about, this is approximately 900 joules here. Now, it fell 20 meters. So within those 20 meters, it transferred all of that potential energy into kinetic energy. So this is almost the same as saying that potential energy after 20 meters is equal to kinetic energy here. So let's figure out what's the potential energy of 20 meters. And this is approximately 200 joules. Another way you could solve this is by figuring out the potential energy at 70 meters and taking the difference between them. So you would get about 700 joules at the 70 meter mark. Take the difference to see how much energy is left into kinetic energy, and you get about 200 joules. All right, number 15. A glass rod is given a positive charge by rubbing it with silk. The rod has become positive by losing electrons. That's the only way you could change your charge is by gaining or losing electrons. You can never change with protons. All right, now we've reached the final stretch of the final 3 questions. Number 16, as a bullet is shot vertically upward. As a bullet shot vertically upward rises, the kinetic energy of the bullet, so it decreases. Think about it, it slows down as it goes upward because of gravity pulling it down. Number 17, a 1 kilogram ball is dropped from the top of a building. Just before striking the ground, the ball's speed is 12 meters per second. What was the ball's gravitational potential energy at the instant it was dropped? So, ball dropped from the top, and at the top you have max potential energy. That's what we're figuring out. And this is at the ground, where you have the max kinetic energy and speed. So from there we can figure out its kinetic energy, which is equal to each other, to the energy wise. Okay. 1 kilogram times velocity of 12 meters per second, and that's squared. 44.5 of that is 72 joules of kinetic energy, which is also equal to the potential energy at the top. Number 18, a rocket with a mass of 1,000 kilograms is moving at that speed. The momentum is, 18 here. Momentum is P is equal to M times V. 1,000 kilograms is our mass. 20 meters per second is our velocity. 20,000 kilograms meters per second is our answer. Choice D. And that's it.